Hello people, welcome back to my channel. So hope you are enjoying the deep neural network series based upon the Python. So far whatever we have learned from the Python skill series based upon the different libraries including the visualizations, we'll be trying to build a neural network, and we'll be using some of the already open datasets that are available from Kaggle and from other websites. So in today's video, we'll be doing or we'll be constructing a deep neural network for digit recognition. So for that, we'll be basically having the MNIST dataset, that is the Modified National Institute of Standards and Technology dataset. So this particular dataset is already bundled with Keras. So you don't need to do a special or explicit import of other datasets like we did in other videos. So that is already there, so that is one thing or one step less that you have to do. And so there are few coding steps that also you want to do, so we'll see all of them one by one. So when we talk about digit recognition, so that is a very vital thing in the real world. So if we have this census data, so since we are having or we are facing this corona pandemic, so many peoples are dying and many peoples at many different villages and regions or households, they are falling sick. So now after some time, when everything gets cooled down, what government will do is they will take the census data. So the last census data was taken in 2010. Now in 2020 we have a gap of 10 years. So basically the government officials will go to each of the households, they'll take the uh, data of each of the people living in the house, the count of persons living, and depending upon the different literacy rates in each of the countries and regions, and also upon the mood of the people, mood swings will happen. So what happens is whenever they input or write any data, it will be reflected in the digit. So sometimes the digit is readable or sometimes the digit is not readable. So that becomes a difficult task even for humans. So for machines, when we build this kind of neural networks, that is also a big kind of hurdle. So we give that activity for neural network. We train our neural network so that it can read such kind of data, that is handwritten character data. Digit data basically will be just limiting to only digit, not alphabets, for neural networks to learn. So it becomes an integral part of categorizing the basic digits. So basic digits in the real world in the literature are from 0 to 9. So you basically have 10 digits. So the classification that also we'll be doing in this will be not binary classification as we did in the Vines dataset. So there we had the predictor variable or a target variable as 0 or 1. So where each of these variables corresponded to the type of wine, red wine or white wine. But here we can't do those kind of binary classification, but instead we have, since we have 10 different classes or 10 different digits, we want to have 10 different classes. So for 0 to 9 digits, we have 0 to 9 different classes. So for 10 digits, we have 10 classes. So for that, we'll be having certain coding techniques that we'll be seeing down the line. So we shall begin this uh, building of neural network. So before that, we need to have certain libraries. So first of all, I'm importing the TensorFlow library as TF, and then I want the matplotlib.pyplot as PLT. So basically for displaying the images. So it has an inbuilt functionality for displaying the images on this MNIST dataset, and this is for displaying the result when you run this pyplot. So in order to show on the screen, you have to run this, because if you are using any outdated versions or like older versions of TensorFlow, it can happen like it may not be shown on the screen. So in order to resolve those things, we basically write this line. And then from the TensorFlow keras we need certain inputs. So first input is the dataset that we want. From the datasets we take the MNIST dataset that is already there. So keras already has certain pre-stored datasets, 3 or 4 datasets. MNIST is one among them, and there is one more that is Fashion MNIST, which consists of some apparels, clothes, shirts, trousers, then ties, belt, shoes, things like that. So that will be seeing in some other videos. That will be more or less same, just a small things like here and there will change in the code. And then we import the sequential for building the skeleton or the architecture of neural network. We have one more variant of this, that is the flexible. Sequential is the simpler one, and so we'll go with this. For adding the units at each of the layers, we require the dense class. So we'll be having that. And finally, we import the keras to this workspace for doing the performance evaluation, or we want to plot the confusion matrix. So for that we'll be basically using this. And then there are two other imports that I'm doing, that is keras.callbacks import early stopping. Now currently in this particular discussion we'll be not doing this. That will be showing in some separate video. Now why early stopping is used, because if you know what are epochs, which I have mentioned in the previous video, we had a small brief introduction what are epochs. So whenever you do the model fitting and then you compile the model and then you evaluate, you observe this transaction log, what is happening. So you get to see what is the loss and what is the accuracy on training and the validation set. So in the first or the second epochs, if your model accuracy is very high, then you can observe like clearly it's a case of overfitting. So in order to save your epochs, basically you do a pre-stopping, that is early stopping. So for that basically you use this. So to save the epochs, you basically use the early stopping. So in the current discussion, we won't be doing that. That will be seeing in some other videos. And then I have something called as batch normalization. So this MNIST dataset particularly, it contains 60,000 different images, that is grayscale images. So this entire big humongous dataset can't be put, or this entire large volume of dataset can't be fed into your neural network. Why? Because it will eventually collapse. So dying neuron will happen, and sometimes there will be exploding gradient or vanishing gradient that is happening, which will be there internally. So in order to prevent all those things, we basically use the batch normalization. We'll see down the line in this video where those things are actually being used. Okay, so since we have spent some time on the libraries that we are going to use, first we'll just make sure like you run this. So if you don't have the latest version of TensorFlow, just make sure you install by this pip install TensorFlow. So it will upgrade your current version of TensorFlow to the latest version. And since I already have that, I'll just print this to check what is the version of TensorFlow, that is mine is 2.3.0. Yours will be different. If you have any older versions like 1.15, you have to then restart the runtime, then only the changes will be affected, else it won't be shown. So make sure that you do that activity before you do the model building. Next what I do is I want to load the MNIST data, and since I mentioned it's already bundled with the keras library, uh, you have this MNIST handwritten digits dataset that is already present. So you just need to call the load data. So that will internally load the MNIST data from the keras library, and on the go it will do the train test split. So if you remember in the Vines dataset, we first created a data frame, then we use the sklearn library, and from that we call the train test split method, and then we do the train test split. So that thing we are doing in one liner, not only loading the dataset, but also we are doing a train test split. But this technique is only limited if your dataset is already loaded into the keras. If you have separate dataset, you have to go and follow that kind of technique, but that technique has certain data leaks possible. Okay, so since we already have this functionality or feature, we'll use this. And we just look into the shape of how my training data is. So if you look this, it is of 60,000 and it is of 784. So if I just run this, possibly, okay. So when I run this, earlier it was showing as a like 784. So now this is basically 60,000 images, and each of those image has dimensions 28 and 24, 28 and 28. So if you want to just visualize, this is something how it looks like. So each image, uh, it's in a bounding box. So the bounding box is basically a square, and the dimension is 28 and 28, and you have 60,000 in numbers. So this is arrangement. So this is the number of data volume that you will be putting into your neural network. So it will be very huge. So we want to convert this internally so that our neural network will do the processing efficiently and it will give us good results. And then what I do is, if I want to see any kind of image which is present inside this neural network, or not in the neural network, in fact in the data set, what I do is I'll call this method, that is IMShow. That is, it will basically show the image which is present, and it will show with the help of the PLT, that is from the matplotlib.pyplot. And from the training image, I want to see uh, what is this particular thing which you pass here, that is basically the value of that particular image stored in that data set. And here, since we're using a color mapping, CMAP stands for color map in matplotlib, so everything will be a grayscale image. So if I just run this, you can see that is this particular digit, if you can make this out, this is 3. So our major objective for building this neural network is to capture the distribution of pixel intensities. So pixel intensities are nothing but the white thing which you can see. So it is very much blurred, as you can see here. If you observe it very closely, you can see the blurriness. But if you observe from a distant point, you can see the digit written as 3. So we want to go into the detail and we want to check how the distribution of each of these pixels are there, and we want to map it to the target variable. Target variable is nothing but the classes which we have mentioned. So for 10 different classes, that is 0 to 9, we'll have that many, for that many digits we'll have that many classes. So this particular digit which you currently see on the screen should be assigned to the class 3. So that is our major objective. And if I just remove this cmap parameter, what you can see is it will show you a colored image, that is the RGB value. But this thing will be not working on because it is computationally intensive, and since we are running on this backend, it will take much of the computation power for the GPU. So instead we'll be limiting our discussion only to grayscale images. Okay, so again I just run this. If you just change these numbers, you obtain different values. So this is something like a 7. Okay, if I just change this, you obtain a 4, something like this. Since we can characterize it much better, that's not a issue, but for machines it becomes a little difficult activity, or neural network it has to categorize. Okay, so internally these digits are stored in a contiguous flattened array. So here I have written 0, 1, 2, 3, 4 in a order, but internally it's not stored in order, they are in random fashion. So it can start with 6, 4, 3, 2, 1, 7, like this. So only digits, but it will be in a random fashion. So this is how internally it will be stored. That's a very long array or contiguous records of different digits. So from this we are extracting one image and we are showing. So in this it will be shown like this, that is pixelated image, that is a pixel densities around each image. Okay, so we just see what is the data that is contained in our training record. So since the data set is very huge, it takes time. So it is in this. So the training data is like it contains digit 5, digit 0, 4, 1, 9, everything. And if you look at the data type, it is int 8. So u int 8. So it is in some form of other format, not the normal integer types. It is of the u int 8 types. Okay, so the file was updated remotely. Okay, our save basically failed, so it is due to the thing that we run on this. So that's why. Okay, so later we'll just check this if it works perfectly or not. Okay, so somewhere down the line we have to do model.save, else we'll lose all the results that we get. Okay, next what we do is we basically want to see what is the distribution of each of the records or each of the classes, basically each of the digits. So for that what I'm doing is, on the training data I'm calling the pd.data frame, and that I'm passing to a variable L, that is the label. So labels are basically 0, 1, 2, 3, those, and I'm just checking the counts of those. So if you look here, so these are like for the digit 1 it is 6742, for 6265 that is for digit 7, for digit 3 it is 6131, and so on. So moreover, if you see over this distribution, you can see say like the data is not much skewed towards a specific digit, but if you just look onto these figures, they are more or less nearby. There is not a huge shift in the data. There is not left skewness or there is no right skewness in the data, but it's moreover uniformly distributed data sets. Okay, so we'll just save the changes here so that it don't give any trouble later. Hope it serves the purpose, because when you deal with this kind of neural networks, this kind of things happen. So sometimes now it is saved successfully. Now it is connecting again, and once it is up we can do the other things. Okay, initializing. Now possibly it should connect to the backend. It depends upon sometimes the internet speed of your locality, and since you are doing the digit recognition for MNIST dataset, it will be taking much of the time. And imagine if you have many lakhs or millions of records. This dataset is only restricted to 60,000. So imagine if you have 10 lakhs or 50 lakhs or even 1 million, that will be very huge. Okay, so we are just connected back to our back engine. Everything should work perfectly. Okay, so what I said before is we have this huge volume of the data that we have. So if we just input this into our data set or into our neural network, it will eventually collapse at some point due to exploding gradient or vanishing gradient. So we want to reshape it. So we already know the reshape thing that we learned from the numpy NP library, and from there we are reshaping this. So we are reshaping the training data on X, and the shape that we are passing is of 784, and it will be internally as float 32. It will be stored in that way, because if you saw here, this data type was u int 8. So we want to change that from float 32. So internally it will be stored in this way. So I'll just run this cell, and for the test data also we want to do the same treatment. And now if I see this shape of this, you can see this is 60,000 and 784. So that is basically the thing which you saw here, that is 28 multiplied by 28, that is 784. So instead of passing three values as a tuple, it will be now passed as 60,000 and 784. So it becomes easier. Now once you did this, we want to represent this to a scale, or to a gray scale, 0 to 1. Now for that, what I did is I just divided this thing. So this is a shorthand operator. And why to 255? Because if you see the digit grayscale images, it ranges from 0 to 255. 0 means the image is dark, and 255 means image is white. So I am just dividing that to a 0 to 1 scale. So all the training data and all the test data, I'm just giving it into a 0 to 1 scale, so that it becomes easier for our computations. Later we'll see why we have done this. Okay, I'll go ahead and just execute this. Hmm. Again it got disconnected. Okay, we'll just run this again. Okay, now it perfectly worked, because every cell should be perfectly working. And just make sure that you don't go back and run any cell again, because if you do that thing, then eventually somewhere down the line, when you run any particular cell, it will throw some error. So just make sure once you execute one cell, you don't go back and you run that again, because everything, uh, or every cells that you run, that will be updated only once. So no pre-run of any cell that is required. Now, as I mentioned, this is moreover like a categorical variable. So since you have 10 different digits from 0 to 9, you have 10 different classes. So binary classification won't work here. So if you watch my softmax video, there I have conceptually described why we require one hot coding. So that was moreover like a theoretical description, or the way how we do one hot coding. But actually in Python, how we do one hot coding. So for that, we basically have this technique. So on the training data that we have, uh, that will be saved to this particular value. From TensorFlow Keras utils, there is a method that is two categorical. So on the training data, what you currently have from above, it will split into 10 different classes, that is 0 to 9, corresponding to each of the digits. Similarly, for the test data on Y, it will do the same thing. So it will be all converted to categorical. So now everything which was there digits, it will be uh, converted everything to categorical variable. So that is basically one hot coding. So if you want to know the details of what one hot coding is, how it is done, just watch my softmax video in deep neural networks playlist. That is a latest video in that. So there I have conceptually described what is one hot coding. One hot coding is basically used in order to save your computational time. So that is the major thing. So this is one coding practice that we follow here. Now since we have done all the pre-processing and all the conversions that we can feed into our neural network, now since everything is perfect, hope so, because nothing is guaranteed, we now draw the blueprint. So first we sketch the skeleton of our model. So model is equal to we are do the instantiation of the skeleton of our neural network. So then we add the layer, that is the first hidden layer. So for first hidden layer, we are using the activation function as relu, that is a hyperparameter again, and the number of units or the neurons that we are passing, that are 784 in number. So that is also other hyperparameter. One notion that you can think of is like, since we had 284 by 284, sorry, 28 by 28 images, uh, we multiply these two, we get 784. So that is one reason we put 784, one justification for this number that I'm putting here. And this on the second hidden layer, I'm just simply putting 10 units, and again the activation function is relu. uh, just we just play around this numbers how we get the results. And then on the output layer, what I have is I have softmax function. So softmax function is basically helpful when you do the one hot coding, so that also is helpful in digit recognition. Okay. And on the output layer, I have 10 neurons or 10 units corresponding to each of the digits that I have. Okay, I'm waiting for this. This is giving me a trouble. So once it is up, I can just run this. Okay, it's initializing and it's connected. I hope this particular thing is run, and I just go ahead and run this. Okay, and now what I do is, based upon the blueprint, I'll just compile all these things. The optimizer that I'm using is Adam optimizer, and here the loss function that I'm using is categorical cross entropy. In Wine's dataset, what we used is binary cross entropy because we have binary variables. Here, since we have categorical variables, 10 different categories of digits, we use the categorical cross entropy. And the metrics, what we want is on the accuracy. So we just compile our model, and here are some initializations, the epochs that we want. Initially we start with 20 epochs, later we change them to see how it affects the performance. And the batch size, we are taking a small batch size, that is 512, and we'll just run this. And then it comes to model fit. So in model fit, we put the train x, train y, the batch size. Currently we have 20, and epochs, the batch size is 512, epochs 20. Validation split, we are doing a train test split here, that is 30% on the validation data, and the verbose is equal to true because we want to see the transaction logs. We want the loss and accuracy on this model, and we just go ahead and evaluate. Okay, so you can see it is executing. So initially the loss is 0.43 and accuracy is 88%, and you can see the accuracy. Just make sure like what accuracy and loss which you are getting, how it is going up or going down, or if there is an overfitting that is present. So currently for 20 epochs it is running. Okay, we have reached halfway, and almost it is touching accuracy of zero point 0.1 because we can make sure like somewhere it is overfitting or something might be wrong, or some parameters we have to tweak certain parameters. That is basically parameter tuning which we want to do. See, accuracy here is 100%. Somewhere it is causing some bottleneck. Okay, the final round is over. Okay, so we got accuracy on the training data as 100%, and the validation we have 97% accuracy. Let's see what are the causes of this and how this thing is visualized. So basically For now visualizations, we basically use this, that is on the history we print the validation accuracy and the training accuracy, and for this we have the same snippet basically from the Vines dataset. So I just go ahead and run this, and if you can see, you have this very distorted, very small box plots. The whiskers are hardly visible. The circles which you can see here, this is for the training, and this is for the validation. So the circles which you can see, those are the outliers, and the whiskers for this are very much touching, that is for on the upper quartile. And because of this, you can see there is a kind of overfitting that is happening in this. So we'll inspect based upon the confusion matrix. So now what I want is, I'll just check the accuracy. Okay, that is 99.3% training accuracy, and on the test accuracy, I have 98.3. And now, based upon this, these are just the raw numbers that we get from the transaction log. Now, our major thing that we want to do is we want to do the performance evaluation. For that, we want to plot the confusion matrix. Now, the confusion matrix plotting or representation will be different from the binary confusion matrix that we had in Vine's dataset. Will be not following that technique, but will have some other technique, because since we have categorical variables and we did one hot coding, we have to do certain kind of other tweaks to this code to make sure that we get the correct confusion matrix. So first what we have is we do the model.predict classes. So that is the same thing. So that we have the rounded predictions for batch size 12 on the test data. We don't put the verbose. These are the basic predictions that we get. So this number 7, or if you run this for this, and if you just run for this, so these are basically the digits that you get. But one problem is that we converted those digits to one hot coding, that is zeros and ones. So if you check this test y, so that is basically an array. So if you just check for this also, this basically is an array representation. So this is still in one hot coding. OHC stands for one hot coding. Now our problem is in confusion matrix, if one variable is in multi-class and one is in other class, it won't be able to plot it properly. So in order to treat that, what we need to do is we want to convert this test uh, data, or which is one hot coded, we have to do the reverse of one hot coding, means we have to convert it back. So in order to convert it back, we have a function that is called as argmax. So it returns the indices of the maximum value along an axis. So to this axis, that is along the row wise, we want to convert this, and this is the technique that we follow. So if I put that is 1 5 here, and if I just run here, you get this 5 and 5 back. So this thing should basically match. If there is a mismatch here, or if you get different values, that means it's still in one hard coding and you have not done that. Now our simple code is to plot the confusion matrix. In confusion matrix we put the rounded labels, that is from one hot coding to the original labelings and the rounded predictions that we have, and we print the confusion matrix. And so this is our final confusion matrix that we get. We can see like on the diagonals for each of the classes. So this is for digit 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So for each of the 9 different digits, we have 9 different classes, and so it presented the confusion matrix. On the diagonals we get a very good true positive and true, not only the true positives which you can see on the diagonals that are very good. On the off diagonals you have very less false positives and false negatives that are present. So this thing, the result which we got is very good. So sometimes by looking at this, we cannot completely verify like it's overfitted or not. But somewhere, if it shoots in the third or the fourth epoch, we can clearly mention like it's a case of overfitting. So this is the current result that we just obtained, and what we now do is we just change this epochs from 20 to 10, and we just change the batch size. And just I want to bring into your attention of one particular thing in this. We'll just save this and we'll just run this. So if you just clearly observe this particular arrow, so this is first arrow, second arrow, third arrow. So that is basically the batch normalization which you do. So why this happens? Because you have 60,000 images and now you have the batch size of 20,000. So 60,000 divided by 20,000 is nothing but 3 batches. So this basically is running in 3 batches. So now it has completed. So first thing which you observe, that was batch 1. In the middle it was batch 2, and finally it was batch 3. So if you look at the accuracy, it is almost 1%. So that is a clear case of overfitting. Even from the very first batch we got that same thing. So if you plot the box plots, it's very bad. The box plots are completely diminished. You can't see any outliers or nothing. That is a very poor performance that you get when you tweak the parameters. So if you have a very large batch size, you get very poor accuracy. So in the very first epoch, you are getting 100% accuracy. That is not a very ideal case that is observed. Accuracy usually it touches 98 or 97%. It's towards the end of the epoch. Epochs doesn't matter, but the batch size, since you increased from 512 to 20,000, it had a clear case of overfitting. So this values accuracy. Don't be happy with it. This is a clear case of overfitting that you get from this. And just for visualization, if you want to check everything visually, what it's correct or not, your analysis is correct or not, you basically plot a visualization. Here on the training side, you can't see any box plot, just only the whisker, or I don't see any, just one particular line I can observe. On the validation set, a very diminished and smaller box plot, which is very bad. And your accuracy is 99.3. It clearly shooted, and on the test also it's same. If you just predict this and just want to see how the confusion matrix looks basically. So if you look onto the confusion matrix, it is more or less same, but it's not good because the visualizations are not that good, because you have taken the training accuracy, or in fact the batch size as 20,000. That's why it just got the accuracy as 100% in the very first. Even on the validation set, you can see it is 97% accuracy. So these are some of the things that I want to bring to your focus. Whenever you do or build neural networks, you have to do certain pre-processing and stuffs like that. And I decided, like, after every neural network session, I'll share a small meme. So that is a new thing. So hope I don't get any copyrights on this. So you did everything this perfectly, but if you just misspelled your import TensorFlow as PLT or pandas as NP, NumPy as TF, you did this kind of thing. So that is the most evilest thing which you can observe. So don't do this kind of mistakes, and just write everything perfectly so that your model will give good results. So hope you guys enjoyed this session on deep neural networks on the MNIST dataset. Hope you guys enjoyed this video. If you found you got educated from this video, please do like, share, comment, and if you are new to this channel, please consider subscribing. Thank you very much for watching this video.